This is the Amp Hour Podcast. Released March 31st, 2019. Episode 436. Downward Sloping Trace.
Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
And I'm Chris Gamble of Contextual Electronics.
After countless audio problems caused by your dodgy microwave oven, just like that SETI signal, they thought they got, wasn't it? From the,
right, well, it was or what about the white label goods that are allowed to emit EMI, right? Like ovens and, not microwave ovens, but like ovens and dishwashers and everything else.
They're allowed to? What?
Yeah, weren't you? I think you were on the show when we talked about that a couple weeks ago. Yeah, there's like the FCC has exceptions for white label goods.
No,
so like certain.
I was not on the show.
Oh, okay. I forgot who I was talking to about that. It was like basically there's like exception items to FCC regulations. So like toaster ovens are allowed to emit. They don't have to be tested, basically.
Right.
So. Well, I made a joke about having like a 1200 watt like RF toaster oven, you know.
Most of those ovens don't even have any digital control anyway. They're just like a mechanical timer or something, aren't they? Some of them.
Sure, but I mean, for I don't know how much longer. So
right, that's Bluetooth and Wi-Fi and
yeah, exactly, and that's what's crazy about it. So like there was a post about that and. In this case, this is actually a microwave oven, which is, near the... I mean, I don't think it actually affects Wi-Fi signals, but it's near the 2.4 gigahertz spectrum, isn't it?
Yes, it's 2.45.
Well, there you go.
But if it's leaking much, then, something's wrong. Yeah. I'd say, it's probably it's probably mains conducted mode interference or something like that.
Yeah, something like that.
Yeah.
Anyways, the microwave in my house may have cut out my signal at the beginning of this, but...
Yeah.
We're not quite there yet, Dave. Wires are still the answer.
You mean it's not the Internet of Things?
It's not. Yeah.
Speaking of which,
we don't live in the future yet.
Ironically, you know how much I groan at the Internet of Things. I'm going to be a judge on the Internet of Things contest. So, yeah.
Really?
Yes.
What kind of contest?
Yes. Oh, it's a design contest. Save the planet, usual spiel. The world's going to shit. Let's save the planet with the Internet of Things, kind of something to do with that.
Who's it for?
A big name. I don't think they've.
Oh, Mr. Secretive over here. Okay, all right.
No, all right. It's Keysight.
Okay. Yep. And everyone is surprised.
And everyone's surprised. I don't know, like they just emailed me last night and they said, "Oh, do you want to be judged?" And I was like, "No." But then they said, like, "Oh, look, we've really got it down pat. So you only have to watch, a couple of 2-minute videos or whatever. Plus, you only spend a couple of hours here." And they seem to have thought about.
Up, man, you just did your contest and you were watching videos for a while, right?
I don't know. Here we go. I'll send you I don't know if it's public. Let me actually have a look. It might actually be a public video. Let me check here. Yeah, it's published. No, there you go.
Okay, all right.
Here you go.
Dave's not breaking any rules.
No. I'll send you the link. And it's like, it's the Keysight Innovation Challenge. Change the world with your smart innovation. Grown. Anyway.
It's tough with all those contests. Like, how do you get anyone's, fine, they're doing a contest, whatever. But even any of the contests are out there, it's tough. These companies want to have, people pay attention and do some interesting work, and they want to reward people. I get it.
It's all marketing. They've got X amount of marketing dollars to spend, and this is one of the ways they use it.
I actually feel for them. Like, we know the Keysight people, but like, it's tough to get attention for that kind of stuff because it's not just like, hey, enter your name in this drawing. It's like,
Keysight are one of the few who actually do corporate videos quite well. They've got Daniel doing the oscilloscope videos. They actually have quite a following on their oscilloscope channel or whatever.
Yeah, they actually have a podcast
that's
too.
Very rare.
I don't know if we've ever mentioned that on here. They have a podcast.
Do they?
Talk,
right.
EE's Talk Tech. Yeah.
Right.
It's not bad. It's a lot of the Keysight engineers.
Right. Yeah, but that's the exception. That's the exception to the rule. Most companies are clueless. It's like, they try and be hip Down with the Kiddies by, starting up a YouTube channel, and they just suck at it. It's just nobody likes corporate
It's tough. Yeah.
YouTube channels.
Yeah,
it just doesn't work. So
I mean,
anyway.
anyone making videos that resonate with people, it's tough.
But anyway, so we'll link in the video, watch it. I think the production value that's gone, I think they've spent more dollars in production value on this promo video than I have for my last 1,000 videos combined. I think
that's almost guaranteed. Yep.
Dollars spent. Yep, guaranteed. I bought a new camera. I've maybe spent a couple of grand or something like. Yeah, they've spent a lot of. They spent a lot of money. It's very well produced. 1 minute 30-second promo video. So anyway, yeah, they've got prizes. You can win 50 grand in cash and 50 grand in test equipment and stuff like that. So
easy, Dave. They're not paying us here to advertise.
No,
Come on.
anyway, no, but our audience can win shit. So and people like entering these contests. And as we said, it looks great on your resume and crap like that. So yeah, enter. There you go. Yeah. I'll be a judge.
Cool.
Which reminds me, I just looked through. I almost done. I'm like 95% done. I looked through all the entries to the Keysight Scope video. I gave away one on my forum, plus there was one where you had to submit a video entry.
Yeah, that's what I was talking about earlier, too.
Yeah.
I saw you tweeting about having to watch a lot of videos.
Yep, and I thought, I'll get a couple of dozen videos, because most people don't want to make, most people are just lazy asses. They just want to go, I'm in to the contest, and that's it. They don't want to actually produce a video. So I thought, I only get a couple of dozen, maybe, tops, and like there's 130 or something, I don't know, 120.
Mm-hmm.
Yeah. Mm-hmm. Oops.
Yeah, that name draw looks real good now, doesn't it?
Yeah, the random name draw. So I watched every single one of them, have a spreadsheet, and I got to copy and paste the things, the names over, and the links and everything, and then comments, and sort of try and rank them. And oh god, yep.
Yeah.
You know what it's like. Preaching to the
hard life of giving away stuff. Yeah, I know it goes.
Yeah. It's just. Well, I tried to give away one on the YouTube comments. I can't even. There's 3 people have not contacted me. It's like it's just pointless, because you cannot contact a YouTube commenter unless they have like a big channel and they have a means to contact you in their about box or whatever.
Oh, interesting.
You can't.
Yeah.
There's
no longer like a mail system or anything like that?
There's no longer a messaging system. No, you can't do it. So you can't send them a message. All you can do is like leave a comment on their comment and hope they have notification is enabled, and hopefully they go check it or something. It's like, it's just, it's dumb.
You should just make another video where you just say their name once, for like a 10-second video. You just say their name. That would freak someone out real bad.
Most of them won't even watch it. They entered and then they forgot all about it. I had 10,000 entries to that.
Damn.
Yeah,
wow.
Exactly. So it's, a good percentage of those aren't going to watch every one of my videos. They're going to forget they entered and... Anyway. Yep. So I think, that's open now, but it's like being judged in like September or something like that. I don't know.
Okay. Cool.
Speaking of September, I have a segue for September, I think.
I thought you were going to start singing September by Earth, Wind and Fire.
No. What? Is that a song? I don't know.
Dun, 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 boom, boom, boom.
No, sorry.
Yeah, it's
no.
Do you remember?
Oh, yeah, I know that. I know that. Right, yeah, okay. Yep, fine.
You're welcome.
Great.
Anyways, well, you go ahead. What's going on in September?
Can we talk about, I don't think we've ever discussed this before, design deja vu. How does this relate to September, I hear you ask? Well, I was cleaning out the old office, and I did a video on I think I put it on the main channel, right, where the death of Electronics Australia magazine, right?
Oh, yeah.
So, anyway, that was quite, a lot of people like that. Anyway, I also found a copy of the May 1996 issue of Elector Electronics magazine, right, which is it's a European thing. I don't know which country. Is it Germany or whatever?
Yeah.
Something yes. I think
maybe the Netherlands. I'm not sure.
Something like that. Anyway. And for some reason I have a copy of this, because we never used to get that here. So I acquired this copy somehow. I'm not sure. And May 1996 cost $2, €2.65 or pounds. No, euros, I think. Anyway, cheap as. What does it cost these days? Anyway, Electro Electronics magazine, and the front cover of it piqued my interest. You know, I was tossing out a lot of old magazines and stuff like that. I know that's bad, and I hate doing it, but I looked at this one, and it had a 64-channel logic analyzer on the front of it. And what's the big deal, you might ask? Well, I'm looking at the photo of it, and it uses the Lattice Semiconductor ISP 1016 chips, which are CPLD devices. I don't think they're current anymore. I don't think you can... Oh, no, you might still be able to get them. But anyway, they were very popular back in, like, mid-90s. So popular that I actually designed an almost identical project and had it published in Electronics Australia magazine on not quite the same date. Mine was actually technically published after this. Mine was published in September, I believe, 1996. This one was in May 1996. And but I've actually done a video on this, which we'll have to link in, where I take you through my old prototype for that logic analyzer, and I got my old handwritten documentation for how I did all the timing diagrams and stuff like that. They're all done by hand. None of this, simulation rubbish, right? Actually got my grid paper, and I'll send you a link to it. And all the timing diagrams and analyzer. Here we go. I'll send it to you. Where is it? There it is. There you go. You can have a look while I'm
what is involved in? I've never thought to make a logic analyzer. I mean, they've been pretty cheap during my career. So
yeah, exactly. Well, back in the day when I was a boy, right?
Sure. I mean, yeah, they used to be really expensive, right?
There was no such thing as a USB logic analyzer, right?
Definitely not.
Yeah, right. Actually, USB. When did USB get invented? Not long before that.
I have no idea.
Anyway, yeah, right. We just take it for granted these days that they're just simple and easy. But back in the old day, yeah, so I designed my own logic analyzer, and it was a 32-channel job, and it used these same Lattice Semiconductor chips. It used the same latch-in A74AC series input chips. It's almost an identical design. It's practically...
What is give us a speed relative too?
Mine was 40 meg samples per second. That was in timing analysis mode. In state analysis mode, I think it was equivalent in state analysis mode. I'm not sure. Anyway, Biggs, if you don't know, you'll have to watch my tutorial on logic analyzers where I explain the difference between state analysis mode and timing analysis mode, which we can go through now if you want to. But
sure, yeah.
Well, okay. Timing analysis mode is how everyone thinks a logic analyzer works. It works like an oscilloscope. It just samples at a fixed sample rate, right? 50 meg samples per second or whatever, 100 meg samples per second.
Right, and big blocky square things show up on a screen then.
Yep, that's it. And it's totally asynchronous to your system under test, right? So if your system is, let's say you have a 50 megahertz clock in your product, and you happen to have a 50 megahertz sample rate in your logic analyzer, then you're not gonna see things.
Nyquist doesn't like you.
Well, even if you have Nyquist, let's say you have a 200 meg sample rate and you have a 50 meg, right? So you've got 4 times there, so you've got enough, right? But then you don't have enough granulation to start then seeing the timing differences between 2 different signals in your particular design. So, of course, in digital design, things like setup and hold time, right? Absolutely critical.
Sure.
If your input transitions at the same time as you're clocking something, oops, metastability, right?
Yep.
I've done a video on metastability. We'll have to link that one in too. What haven't I done a video on? Jeez. Anyway, an infinite amount of stuff is the answer to that. Anyway, so metastable. So when you're trying to debug your design could have metastability problems. It could have setup and hold problems and stuff like that. And to do that with timing analysis, you really need a very high oversample rate, and then you've got drifts between the clocks as well as they slowly drift. So if you're sampling at 200 meg samples per second and your product is at 50 meg, it's over time those 2 clocks aren't precisely synchronized, right? So they're going to slowly drift with respect to each other. So your product might be working on your logic analyzer. It might look like it's working 1 minute, and then a minute later it might drift out of the sample window, and boom, it looks like all your signals are suddenly doing something weird, right?
I had a former firmware coworker that I worked with who was like really, really adept with this old HP logic analyzer we had, and a lot of times we're like, he'd be like, well, he'd be like trying a bunch of different things, and he'd go back and forth, back and forth, back and forth, and finally I was just like, look, can I just throw a scope on there real fast? And of course, the logic analyzer he was really used to, and exactly.
Yeah.
It was somewhere in between, states or timing or something, and it was really obvious at that point. But, and of course, my answer was always to put a scope on it anyways. But like, not like it was like really original.
Check your signal integrity first.
Yeah. But I mean, I think it happens a lot where you get lulled into that false sense of security, and I think people with people with even like a Saleae, they'll recognize that too, where there's like, you have the digital channels like, oh, something weird's happening.
Yep.
You have to at least recognize that are you looking at noise? Are you looking at some kind of actual aberration, or is it just that your samples are way out and you're throwing some other kind of gunk on screen?
And you can come a gutsa with that too, even if you know about this and you're very careful and you set up the correct logic thresholds. Let's say you're working with TTL and you set up the proper TTL logic thresholds, right? The actual low and high voltage levels are precisely what they should be. Well, there can be small differences between that theoretical logic threshold and what your actual logic is doing at that particular temperature with that particular grade part, blah, blah, blah. Right? So even if you're super cautious, you can still have minute differences there, which can cause you, weeks of troubleshooting, trying to find this elusive problem because you've got this little runt pulse that just goes up and just meets the threshold, whereas your logic analyzer doesn't see it. So, that could ruin your day.
It's crazy.
But anyway,
definitely.
So that's timing analysis mode. That's how almost everyone uses their logic analyzer. But sometimes when especially in computer systems and stuff like that, like really high-end ones, if you're designing an Intel motherboard or something, and you're probably going to be using like maybe a synchronous system where the logic analyzer will actually have a clock input, and you put that clock to your master clock on your product so that the logic analyzer samples in synchronization with your product sample clock. Either it could be, if you're debugging FPGA, it could be your FPGA clock or something like that, or any other clock within your system, and then that gets away any problems with clock drift or clock timing. You can really properly see setup and hold times and things like that. So you can see, oh look, this input here changed at the same time as this clock on your product, and oops, there's no setup time there. We don't have enough setup time and stuff like that. So, that's why logic analyzers typically have state and timing analysis mode. And typically, state analysis mode will be a lower sampling rate spec than the timing analysis
because it's actually using
mode.
some of those samples that you would have used otherwise, where you're just blasting the data in, that kind of thing.
Oh, it's an architecture thing. We won't go into details, but typically the specs might be different. Sometimes they're the same. I think on my one it was the same. I don't know. I'd have to go through my original design. But
got it.
Anyway, I found it fascinating. Deja vu. Like, there's no way we could have copied each other, right? I didn't copy them because I didn't even get Elector magazine, and all my design stuff is dated back in November 95. So a good 4 months before this design was published, and you can see that in my videos, right? And they couldn't have copied me because this one came out in May, and mine wasn't published until September. Right, so it just so happens that both of us
it's like,
decided to do it. Yeah,
Leibniz and what's his name? I'm not giving you that much credit here. It's not like he invented calculus, but
right,
sometimes just like the confluence of like if the part was affordable and it was a good fit, maybe there were similar projects out in the world that inspired you and that other author to do the same thing. Yeah, totally possible. Probably more common than we think.
Yeah, of course, and that's what I want to know. Does anyone have a similar deja vu design story? You know, did you design something, then somebody published something the same month or came up with exactly the same product or something like that? But I can tell you how this happened, right? Because you've got to look at this, right? The guy would have developed this in 95, same as me, right? End of 95. It was published in May. And so we were designing this at virtually the same time. And back then, it starts with the idea, I want a PC-based logic analyzer, right? So obviously, 1,000 people could come up with the idea for a PC-based logic analyzer, right?
Yeah.
No problems whatsoever. But then how do you implement that? And you look around and going, well, I could do it with all discrete TTL, but holy crap, that's a lot of TTL.
Yeah, that'd be kind of rough.
That's a lot of discrete logic. You can do it, and a lot of old school magazine logic analyzer projects did that. So, but then so you get the idea, let's use one of these newfangled programmable logic devices, right? And you can't use a microcontroller because microcontrollers aren't, determined. They're not fast enough, especially back then, right?
Right.
You can't get hundreds of megahertz microcontrollers like you can these days, and they're not deterministic.
Are you saying because you would have had to like oversample it so much, and you would have had not oversample it, but because you
couldn't even do that. You couldn't do it with a logic analyzer. A microcontroller. It's just silly. Right.
I just mean that because you don't know how many cycles it'll take going through the ALUs and all the other stuff.
And all that sort of stuff. No, it's just silly. So the only sensible solution is to use like hard-coded logic to do it. So you either use discrete or you use programmable. And when you look at the programmable logic scene back in 1995, how many years? We're talking 24 years ago now, right? 24 years ago, right? Yeah, FPGAs were around, but holy crap. Right,
if you're in the military and you're
they're expensive.
Got, 20 grand to spend, right?
Ironically, a now friend of mine, he was developing a logic analyzer at the same time, once again for publication in Electronics Australia magazine. But I beat him. My project scooped him. He published it like 6 months after mine. But his one was based on Altera FPGAs, I think it was. Or, I don't know, it could have been Xilinx, whatever. Anyway, it was FPGA based. It was really high end. But that was his day job. Like, he was a certified FPGA professional for Altera or Xilinx back then, right?
Yeah.
And so he had access to the multi-$1,000 development systems that you needed.
Right. Because you also couldn't get dev boards without contracts and
yeah, exactly. You need, like, they wouldn't talk to you unless you're a big deal. Pretty much. So he had access to FPGAs, but your Joe average, basically, in 1995, you did not use FPGAs. So even CPLDs were quite hard. And Lattice actually, by hard, I mean, you couldn't buy cheap tools. You couldn't, the software cost money, all that sort of jazz.
There was no open source tool chain in as many words, right?
Yeah, no, there was no open source anything, right? And so I think Lattice came out with their CPLDs, this series, the 1000 and series, 1000, 2000 series CPLDs in probably a year before that, and they were one of the first programmable logic companies to actually target hobbyists in the hobby magazines, right? So you'd see the ads in there, a full-page ad. Oh, these Lattice, 1016 CPLDs. Here's a development kit. And they give you a couple of sample chips, and they give you the software for free. And, the kit cost $100 or something like that, but it was affordable.
Sure, but reasonable compared to the thousands.
It was reasonable cost compared to the thousands for the FPGAs, and you could make up a little parallel port interface cable for it. I don't know. They may have even gave you one, right?
I was wondering about that, like how you actually got these signals back to the computer, but I guess parallel port.
Exactly.
Kind of the answer a lot of the times those days.
Right. So that was pretty much, so those Lattice chips in 1995 were pretty much the only choice if you were looking to develop a product like this, unless you had access to higher end, stuff available. And you could buy these Lattice chips from like RS Components and stuff, right? You could actually buy them.
Yeah.
They weren't particularly cheap, but you could buy them and you could program them. So you could sell kits with the programmable chips. You didn't need a $5,000 big, data I/O programmer to program or whatever. You could just program with this parallel port interface cable, or was a serial port, whatever it was. And so that was cool. So that's how we both ended up choosing that chip, because it was the obvious choice. And then we both went, well, how do we get data into the PC? And we went, well, parallel port. How else would you get,
Right.
how else would you get your data back into the PC in 1995? When did USB come out? I'm looking at 94.
Yeah, I don't know.
Hang on, 90.
Yeah, but that took a while to like propagate too. I mean, I remember early.
It began
early PCs
development
had
in
lots of
94.
cables that were,
Yeah. So
I think that is the crazy thing too, like like how ubiquitous. I mean, you and I are both talking USB microphones right now. That's not that unusual.
I'm
I mean,
not
like
actually. It's not a USB, but it's a USB Rode interface box
Sure,
though.
sure.
Yep. So
oh, that's true. Yeah. Okay. So your A to D is connected to a
my A to
you know,
Ds. Yeah.
yeah
exactly.
USB system. I mean, it is. It's crazy it's become so much of a standard. But I guess that's
There
that's
it
what
is.
happens.
It was released in 1996. So there you go. It was like USB had literally just come out, or when we were both developing this project, it had not come out. So we didn't even know about USB. It wasn't a thing. And then it would have been USB 1, and then what,
and those
what
chips would
software
have been
tools
super
were
expensive too,
oh,
right?
super expensive, right?
Yeah.
If you could get them at all. Like who the hell was, your average hobbyist midnight engineer wouldn't be able to get a USB chip in 1996 when it first came out, let alone the software and the libraries to interface to it and all that. And then you would have had to put a smart microcontroller inside your product, right? So
Right,
it's
right.
just
Up in your
like
cost
nuts.
all around,
How do you do that? You take it for granted. You just buy a microcontroller that's got USB built in and all the enumerations done, and
Yeah, I mean, I was talking to someone that's a lot of chips these days have like just even USB bootloaders. So you basically hook in your D plus D minus into the micro, and it's already got a bootloader preloaded on there. It's like, damn, that's crazy.
Yeah, it's
it's
nuts.
awesome, but it's crazy.
So in 96, this wasn't available. So we both chose the parallel port, and then we both chose the same number of lattice chips and broke them down in the same thing. We had one chip devoted to mine was an 8-channel sampling front end. I think his was a 16-channel sampling front end. And so that did all the masking logic and all that sort of stuff. So if you look at it, if you look at the schematics, the internal schematics of both of our input sampling chips, input masking and all that, they're basically identical. How do you do that? You feed data via a shift register into a mask array, and then you have a big number of XOR gates, and then you feed each signal in, and you can either mask it, you can trigger on high, low, or don't care conditions for each of your channels. So it turned out to be an almost identical schematic when you look at it and you go, these guys must have copied each other. And it's like, no, it's just, it's just the natural progression.
Sometimes there's only so many ways to do a thing,
Yeah, there's so many obvious ways. And then we had one control lattice chip. And so the two projects look near identical. I just find it remarkable.
Now, does you make your skin crawl thinking, oh man, I wonder if someone's out there making a microsupplier right now, exactly the same.
I think they are. Isn't there there's probably a Kickstarter or something, or an Indiegogo or something
probably.
At the moment.
Yeah, I mean, at the end of the day, it doesn't really. We were first talking about like hobby projects and things that are published, and it's like that's a little bit different. But like at the end of the day, most of the time it's the marketing that matters the most. It's like it's the stuff that we don't want to think about, but there's usually the truth. It's that a lot of auxiliary things matter a lot more than we give credit for.
Indeed.
Sales channels and all that other crap.
So,
but you are moving on with your design. So you wanted to talk about custom heat sinks.
Yes, because the video will be released tomorrow. My patrons have already seen it, and I sent you the link, so you've at least had a 2-second poke at it. And how to design custom heat sinks, because I don't think anyone's really done a video on that. So as part of our
I haven't seen anything
supply,
like that. It's good though. I mean, it's like I've made some content in the past about like just commercially available heat sinks from DigiKey and Mauser and a lot of the distributors, but thinking about like actually that next step to make something custom, it's like I would never probably suggest that for my students, because usually they're beginning electronics, but I think that it makes a lot of sense as you move forward.
Well, that was the point of the video.
Yeah, right.
Was to encourage people, look, hey, at least consider the idea that yes, you can do your own custom heatsink if you have to. If you've got a unique product like this microsupply is, it's a pretty pretty demanding form factor with pretty demanding thermal requirements and stuff like that. So it's not your average project where you can get away with an off-the-shelf heatsink, really. But
and I think the other thing is that the off-the-shelves they force you into a certain like form factor as well.
They do, exactly.
Yeah.
But I've often said that can be a good thing. Like you choose when you come up with a project idea, choose the case and then mold your project around the case. That can often be quite a valid design, a way to actually design your product. Some people go, oh, I never do that. No, write the specs first, write, drawings of what it's going to look like and design your custom case, blah, 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 blah. And well, yeah, okay, that's one way. And that's what we're doing with the microsupply. But because everything's custom on this.
Sure, right.
So,
but I think once you start going down that path, it's like,
you go the whole hog. Yeah.
Right.
Once you,
So like if you were going to go all off the shelf, right? You go off the shelf case, you go off the shelf heatsink, you go off the shelf whatever else, standoffs,
off the shelf connectors, standoffs, front panels,
all that stuff, right?
Yeah.
Then it's like you get a certain look, and that's fine. But I think one of the things that I think about is like, especially in like modern product design, is that you have a lot of air. You know what I mean? Like it's just a lot more. Your product is a little bit bulkier. It's less sleek. You don't have as much, form factor type of stuff. And
I call that volumetric efficiency.
Yeah, there you go.
Which is, but yeah, I don't know if that's an industry term, but that's what I call it. It's volumetric efficiency. And I talk about that in my videos all the time when you're laying out products and things like that. And the microsupply has a ton of that, a ton of volumetric efficiency. It's very efficient in terms of the volume it uses. It's not 100%. We could technically make it smaller, but
Right, but it's a design choice as well, right? You don't have to make it that small. Like I don't.
No, that's right.
You're trying to make a handheld, so that definitely informs some of this stuff of like, okay, you don't want it to be like a half-meter wide box, or something like that, because you want to actually make it handheld.
Because people are used to people hold things in their hand all the time. They're used to things being a certain size, weight, and form factor, right?
Yes, that's right. Yep.
And
I think, and then that then kind of, and that's because that's a priority for you. I mean, hell, even just having micro in the name, right? It's it says it's not going to be too big, and so then that kind of just ripples all the way down the line, and it's like, well, you could have put a different heatsink in, but because you favored the form factor more than other things, you couldn't use the stuff off the shelf. So at that point,
that's right.
Makes sense. Yeah.
And we all make these value judgments all the time. Like you pick up one of those newfangled phablet things and you go, oh geez, that's too big. You pick up a new or you get a you pick up you pick up a new multimeter and you go, oh geez, that's just too big. Or you pick it up and you might go, oh, that's small and compact, isn't it? I really like that. You might find it surprisingly small or surprisingly big, and you make these sort of calls all the time. And and it can be.
But then that's a forcing function on everything else, right? It's it either makes you stand out from the marketing side, or then you have to go and start buying parts that are necessarily small, and you can't put extra, features in, all that other stuff. I think personally, I've always been like, if I have the space, if I have the way to do it at the beginning, I'm gonna make it bigger, just because. Shrink it later.
Allow for expansion during the design or upgrade phase as well. We've got spare room on our PCB. We didn't make it so if we have to change some stuff, there's we can shuffle things around, and we've got extra room there. And we didn't start out with a dimension. We didn't go, it must be this dimensions and make it that. We just sort of started out like look, the LCD has to be this big, and it's got to do X amount of power. It's got to have these X converters in it, and sort of you start mocking up your PCB layout, and a form factor just pops out.
Sure. And I think the power envelope's another big one too, because like sometimes you're just gonna be like, well, it's gonna be 100 watts. Can you even hold it in your hands? It's gonna be 1,000 watts. Can you hold it? It's just like certain things are things that you've understood from years of design, right? But like just that intuitive testing of like, okay, well, if it's gonna burn this much heat, then what's the temperature rise gonna be? And in your case, is someone gonna be able to hold it in their hand? That kind of thing. So.
And that's the interesting part. All the thermal decisions in this thing and why we went with the custom heatsink. The original design was actually to use an extruded aluminium case, right? Which are
and then you're
like
gonna heat sink
cheap,
to the case.
simple. Yeah, and you can get those made custom made really cheap with hardly any tooling cost, right? And
Right.
and they're great. Yeah, you can use the case as a heatsink. And I've done a whole video on that, which another one we can link in, which is actually, I think that's a really killer video. I go into tons of detail about thermal resistance of vias and transfer and sill pads and all sorts of stuff from surface mount components, like surface mount power transistors, to external cases, right? And how to get that heat out of your product. And in the end, for various reasons, we decided we were led down the path of why we went away from the extruded aluminium case, because it was really hard you had to slide things in, and the screen didn't work, and the keypad didn't work. Like lots of things just weren't working. So we went, then we could maybe use a split design, and then, if we're going for a split design, and so we ended up, bugger it, let's just do, it's going to be cheaper to do a custom ABS case, right? So we just we made the decision, right, we're going to be a completely custom case, but now our case is plastic. So we can't use the case as the heatsink anymore, so we have to put a heatsink inside. You can do it once. It's not even going to be great once.
I had a fun I had a fun lesson in thermal efficiency today.
What's it?
Just as a brief side note, we'll come back to this. So like I was doing I had a bunch of metal standoffs to like get the boards. I was doing a reflow, and I was getting the boards up off the deck of this reflow oven, and so I had like 4 sets of standoffs. So I get the board up, and then the 5th one I didn't have, and I just needed to like prop up one side, and so it was really stupid. And so I was thinking like, oh well, I have. The dog here does not like the story, as you can hear. So I have these old connectors, and they're plastic, and they survive being in the reflow oven all the time. Right. I'll just use one of these connectors to prop up this board. And so like I go through the whole reflow process, and I'm like, what does that smell? Mm-hmm. And it turns out that the reason that the plastic connectors survive in reflow ovens is because they're not touching anything that actually retains heat. They're just touching air. And when you have them touching something like FR4 that does retain heat, plastic melts real fast. So I have a board that has a plastic connector melted to the back of it. And so there's a little lesson there. Don't use old connectors as standoffs in the reflow oven.
Well done.
Yeah.
Have to do a golf clap.
Yeah, it popped right off of there. It was not a big deal, but it was
right.
It was a quick little lesson in thermal efficiency and in one-time use of plastic as a thermal sink.
Right. So how do we get heat out of a plastic case, Mr. Gamma?
With some metal.
With some metal.
And air.
Yeah, exactly. What sort of air?
Forced air usually, but
that's
also
forced convection. Yeah. Well, you can't have a fan in a little handheld thing, can you?
Right. So what's the other one? So there's radiation, there's forced convection, and then there's the third
convection. Natural convection.
Yes, that'd be it. So that's what you're going to be doing is natural convection.
So to get natural convection, yes. To get convection, you need air, like a place for the air to flow.
You need holes in the container.
You need holes. So they get, so you put vent holes in the back of your plastic case, and you design your heatsink so that the fins on there match the orientation of the slots on the back of your case, because if you put them in the opposite orientation, then air can't flow through along your fins, because that's how you get heat off your heatsink, as the air either
you
forced
increase
or
your
natural.
surface area, and you want to have these channels that the air flows down, right?
Yep. So so we whacked that on the back, and Bob's your uncle. We've got our.
Did you guys do like maybe it's too advanced, I don't know, but like did you do like computational fluid dynamic stuff? Like I know that people do that.
No. We actually haven't tested this heatsink yet, which is what I mentioned
TBD.
in the video. But
Sure.
But but by rules of thumb and some basic back of the envelope calculations, it's going to be more than good enough. It's not right.
Well, you're not worried about actually melting the case or anything like that. You're probably so like what kind of, and I like you said, I didn't get the chance to see the whole video before. I was just watching snippets of it. But like what kind of like temperature rise are you expecting? Even a worst case scenario.
I didn't actually mention that. I didn't go into specific details. It's just
got it.
Like,
yeah, because I mean that's
custom.
stuff like it's like so it's what the power envelope, like how much power you expect to burn on the heat sink, and then it's also how much surface area you have, and then the thermal conductivity of the heat sink, which should hopefully be perfect, but is never perfect.
And then they couple in air to you know, and they have different specs. They have different degree C per watt specs for both forced and natural convection. And
then I was thinking
like
of the junction to case thing as well, but that's at that point you don't really care as much, right? So the junction to case
they're
is
usually reasonably low, you know. So,
right.
Yeah. It's mainly the efficiency. It's mainly the size and the efficiency of your heatsink, of the fins and the bulk of the material and stuff like that matters as well. So you can't just make these things. You know, a lot of people think you can just I just put like a large big copper pad on my PCB as a heatsink for my power transistor. Yeah, you can at quite low powers, but they're actually very inefficient because they're so thin. Like, because a 1 ounce copper board is 35 microns thick, right?
That's right. We talked about that last time.
Yeah, that is really thin, right? So heat really doesn't get to the outer, like over the surface area very efficiently. So it's quite poor.
Right.
And
what if you did like when solder has no flux left in it and you have like the whiskers that pull off? What if you just like put that on and then you just kept like pulling out like all these little spiky whiskers? That would probably help a little bit on surface area, right? Like on
right. Well, you can actually. A lot of people solder coat.
Yeah, I've seen that before.
They'll solder coat the things to make it, just to make it thicker, a bigger thermal mass, and a better thermal transfer medium. You know, that's a thing. Back in the day, you used to rely on the fact that your board was wave soldered, so you just leave your solder mask off, and then you'd get all your wave tin plate on top of your big, your thermal pad.
Yeah.
So yeah.
Oh, I want to ask you about exposed thermal area, or exposed copper area after this.
Yep.
Yeah.
Oh, as in private or?
No.
After
as
this.
in,
Okay.
as in you made a big video about a KiCad with the thing around the edge.
Oh, okay. Yes. All right.
Yeah.
Now, I
have many notes for you, my friend.
All right. The last thing about this heatsink, right, is that we designed it, and what I recommend in the video is if you're going to do your own heatsink like this, or your own case or whatever it is, your own little widget. For your product, if it's custom, make sure you design it so that it is machinable in the case of metal, right? So it's machinable as a prototype, or it's 3D printable in terms of like a plastic case or something like that, right? So even if your final thing is either going to be die cast or it's going to be injection molded case, which is the case with both our heatsink and our enclosure for the microsupply. The heatsink is going to be die cast, so we need a mold for that, and our case is going to be injection molded, so we need an injection molding for that.
Right.
And
you're saying don't wait till the end to make sure you piece everything together. Is that what you're going to do?
Well, that's it. And you don't want to pay that tooling, right? Because it's expensive to buy molds, right? So you don't want to do that just for your prototype. So that's why we designed it, so that it's compatible with either a machining process, this heatsink, either a machining process or an injection or a die cast process as well. So we went and got this, instead of paying $1,000 or whatever for a mold and then get die cast one prototypes back, we just went to a machining house and said, please machine us 4 of these. So we ordered 4 of them. They cost $60, $65 each, right?
That's great.
Which is an expensive heatsink one-off, but it's dirt cheap compared to the cost of a mold. And now and there will be virtually zero difference in both terms of physical and thermal performance between a die-cast version of this heatsink and a machined one. So we can do all our proper tests. But you can get the die-cast anodized, right?
Yeah.
So, there'll be virtually zero difference. So we can use a totally different process to get it manufactured and still be virtually 100% confident that it's going to be fine when we go. And so when we push that, when we test our prototype, we can go, right, we need to push the production button now. Okay, let's buy our mold. Let's get our die-cast mold and spend our tooling cost and be pretty confident it's going to be fine. So, yeah.
That's great.
Yeah, it's great.
What is so I was going to ask you about like your rule of thumb as well. So what is a decent temperature rise in your opinion? So you're not going to have a fan in there.
Yep.
So what about like the
10 to 20 degrees? 10 is probably like, once again, it depends on the product and what envelope you're going to be pushing it. But a industry rule of thumb is a 10 degrees C rise, so that basically, because most operational ranges for products are like 0 to 40 or something like that, right? So if you've got a 10 degrees rise, and that puts the heatsink at 50, or even a 20 degrees rise, or even if you've got a 0 to 50 degrees operational range, puts your heatsink at 60, stuff like that, which is just above the borderline of when it's like hot to touch, like burning, kind of. Yeah, you don't want to be running it at 100 degrees. If you're running your heatsink at 100 degrees, unless you absolutely need to, for some particular performance, versus volume thing or something like that, right?
Right.
Then
and even still, you probably
wrong.
can't do that the whole time. Yeah. You're going to start degrading quality.
Rigol got this wrong, right? I've done a video on this. Rigol, their power supply, their DP832 power supply or whatever it is, right? I did a video actually analysing their thermal design of that thing, and they were running their heatsink at like 120 degrees. And that was like borderline to the actual...
Yeah, that's like the junction problem.
The junction cutoff temperature, where the thermal protection would kick in. Right. And it was insane. Right. It's like, who the hell does this?
So if people don't know, too, the reason that these temperatures exist is because at certain temperatures, you start to have like ion migration and breakdown inside the actual die. And so like... you basically break your parts at a certain temperature. That's the same thing happens if you short out a part. I mean, well, there's other problems too, but if you short out a part, if it's dying by magic smoke, oftentimes it's because of thermal breakdown. It's just going poof, it burns up. And and sustained high temperatures like that, you start to have like ion migration and all kinds of bad stuff happening inside the silicon, and then
that can ruin your day.
Yeah.
And as I said, like regulators and stuff like that will have thermal overload protection on the die.
Exactly. Yep.
Right. So they'll simply shut down and go, oh, no, I can't work anymore.
Mm-hmm. Well, that's a good rule of thumb though. 10 to 20 degrees.
Yep.
The other thing I always think about too is that like so that's like your temperature rise stuff. I mean, the thing I always forget about is it's like, some people live, I mean, you live in a friggin' hot place. I live in a very cold place. You live in a very hot place in the summer. But then like ambient temperatures, you always have to add that stuff up. And then you start to move outside of operating ranges pretty fast too, right? So like a lot of commercial parts that you're buying are 0 to 85, right? Mm-hmm. And so you have a 45 degree day in Sydney, right? You have
and you got a 40 degree C temperature rise designed to be a product. You're,
right. And I mean, in your case, you're making test equipment as well, which, there's temperature rise, but then you also have to derate as well. So like, okay, so now it's 45 degrees in Sydney again. Mm-hmm. For some reason, you're outside in the sun, in the Sydney blazing summer using your micro supply. You've got a 20 degree rise there, and I've actually just got heat stroke thinking about this, so I've lost my train of thought. Oh, that's what it was. You so you start to lose accuracy as well, right? So you've got your inside your cases at 65.
Yeah.
You've got a sense resistor in there that's 0.1%, but you got all the temperature problems, and all your errors start stacking up.
I was going to mention resistors. I've done a video on this way back in the garage, where if you go to like a data sheet for a surface mount resistor, okay, an 0603 or an 08F5 resistor, for example, can dissipate a quarter of a watt. Okay, right? So people might not think about it. Oh, it can do it's rated quarter of a watt, right? A standard quarter of a watt resistor, axial resistor. Right. Yeah, go look at the freaking data sheet of what temperature it runs at that quarter watts. It's like 100 degrees, right?
Right. Yeah.
Right. It's not going to run like cool at that. That's its maximum rating. So this
it can do a quarter of a watt. It'll survive a quarter of a watt.
It'll survive a quarter of a watt, but it'll be running literally at 100 degrees Celsius. Right? Or it'll run at 100 degrees above ambient, whatever the current ambient is. Go and read the data sheet.
Yeah, it's crazy.
It's like, it's nuts. Right? And people think,
times your temperature coefficient.
Put in a quarter resistor,
Now what's your 10K resistor is now a 15K resistor or whatever it is, another direction probably.
Oh, it's not quite that. Jeez, how many ppm are you talking? You're not talking about parts per million. You're talking about parts per milli or parts per
parts per deci.
or just parts.
Yeah.
Parts per degree C, not parts per million. Jeez. 10K change it to 15.
It's called hyperbole, Dave. It's called hyperbole.
Engineers don't talk in hyperboles.
Yes, we do.
No, we don't.
I was going to bring up too. You Yeah, you were not here last time, unfortunately, but the with Andreas, he kept talking about how "it depends" is a very expensive phrase in business, and I was thinking about you every time because you always say that.
I always say it depends. Well, it does. Everything depends.
It does. But if if you're trying to, he was talking about it in the context of business practices, because he does,
right.
That's his background.
When your designer says, you ask your designer, oh, how long is it going to take to develop this thing, and they go, it depends, then
Right.
you're,
Yep.
that's when you're screwed.
Yeah, right,
So,
exactly.
Yeah, but that's the art of engineering, taking the it depends part through to its conclusion,
Yeah,
and doing
right.
what needs to be done to, narrowing that down.
Well, that's exciting about the custom
Yeah.
heatsink though, and those machine samples you showed, that was good too.
Oh, they're very sexy. Yeah, they're beautiful machine samples. I think they're cheap.
You're doing it all
$60.
wrong, Dave. Come on, man. You say, okay, I need a heatsink. You go design the heatsink. You say, okay, well, I want to make it machinable. And then what you do is you stop everything you're doing. You take 6 months and you try and teach yourself how to do machining. You're doing it all wrong, my friend.
Right, because technically I do have a milling machine here. I just have to finish assembling it and get it working and learn how to do it. Yeah.
Don't be like me, Dave. Don't be like me.
You're still recovering from your learning to mill experience.
Yeah. Yeah.
It's just like it's like assembling. It's like having your own pick and place machine. It's just like for 99.9% of people, it's just not going to work. It's just going to suck your time and your soul away.
Right. Well, and I think it's so that's like a very, very extreme version. So like some people are going to go and buy the pick and place or build a big pick and place machine or build the mill or learn to mill or whatever it is. I think even from your example, taking a step back, most people who are going to watch this, yes, they can do a custom heatsink, but I would not suggest starting there. I'd say go and find a heatsink to start with.
Yep, absolutely.
But this is a good intermediate to advanced topic that I think it's good to showcase.
Yeah, I just want people to, at least have in the back of their mind that, hey, it's not that expensive or hard to actually do your own custom heatsink. And, hey, that might make my product a lot better, right, in terms of form and function.
Yeah,
right? It could make your product from, that looks okay to, wow, that looks amazing. And that could drive sales an incredible amount.
I don't know if I agree with that, but I think it does make the. I think it makes the product better.
It depends on the product.
I've never heard someone say, I'm going to buy that for the heatsink.
No, but come on, you know what I mean? Like the form factor, right? If you do a custom heatsink instead of off the shelf one, people might go, "Oh, this is big, thick, and chunky. That's not really a handheld thing." And you show them one that has a custom heatsink and it's half the thickness and it's or whatever. Then they're going to go, "Wow, that's."
I think you're like half right. I think you're right about the form. The form is definitely a thing that people are going to be like, "Oh, wow, that's different and cool and whatever." But I don't think most people, as long as it performs to what you say it's going to perform to, I don't think most people care about the fact that it has a custom heatsink in there. Because if you did it with a off-the-shelf heatsink, they wouldn't care as much anyways. You know what I mean? It's just the form sells it.
Depends on your market.
But
Depends on your market.
Yes, I know. Yes.
Right?
Yep.
Is it consumer versus engineers? Like there's a big difference between consumers and engineers in terms of market.
Right.
There you go. So anyway, we've got custom everything on this. We've got custom heatsink, custom case, custom screen protector, custom LCD, which you've seen the video on, custom I say custom LCD, custom planar transformer. We've got custom banana connectors, which actually didn't really cost us any more. The manufacturer said, "Oh yeah, we can just make these little changes for you. Shouldn't be a problem."
And stay tuned, folks, for Dave complains about sourcing issues in about 2 months from now.
Yeah, and I'm not done yet. And then we've got custom little clips to interface the banana plugs to the PCB.
It's great, man.
Stuff like that. So
I can't wait. This is going to be fodder for the Amp Hour for months. It's great. It's brilliant. It's brilliant.
Years of fodder.
That's right.
Fodder.
Yeah. It's nothing if not a marketing exercise.
Yeah. Anyway, it's just it's very cool.
Speaking of design, though, and I guess custom things.
Oh, did I mention a custom keypad too? It's got everything.
Yeah, everything. Is it done yet? So I saw you using KiCad the other day. You're back. You're back on it, man. It was good.
Because my file happened to be in KiCad. Not KiCad. None of this KiCad rubbish. KiCad.
KiCad. You call it tomato, I call it tomato. I don't care what you call it. Yeah, it was good. It was a good look. It was a good look at the latest versions, and you missed one button.
Long and waffly. Which button did I miss?
There's a VIA button. That's what I was kept trying
place
to...
VIA. No, I specifically said in the video, you weren't paying attention. I specifically said in the video that I didn't want to place a VIA. I wanted to copy and paste for reasons of doing bulk lots, right, and getting them all lined up. See, because when you're doing something, when you're stitching around the outside like this, of course, just due to engineering perfection, you want them all to be nicely, evenly spaced, right? And you can have hundreds and hundreds of vias surrounding your board or stitching your ground plane or whatever, right? And you don't want to go placing them one by one with the via button or the via shortcut or the via placing tool, because then you've got to manually place them. So what you want to do is manually place a couple of them, and then copy and paste them into bigger arrays.
Yeah,
there's these,
okay. So
right?
there's another thing. There's the create array. There's a create array.
Okay.
So
right. There's a create, and that works just on the vias, does it?
Yep.
Right. Okay.
It's like small things.
See,
like
that's
that.
a different thing, right?
It is, but it's because you were struggling with the thing that I like about the VIA button is it's very similar to Ultimate, is that it grabs the ground plane that you're on top of, or whatever plane you're on top of. So
right, yes, yep. I realised that, but I wanted to copy and paste because that is a legitimate design technique with lots of advantages, right? You don't, right? There's many reasons why you want to do that, and
Dave, I'm not criticizing you, man. I was just saying what I was talking to the screen when I was watching it.
And I'm just saying this is just why I highlighted it, because that's a missing feature. I presume it's missing in KiCad, is that when you paste something, when you paste a VIA, it doesn't take the net from the plane that you're placing it on.
Yeah, I'm not sure.
Yeah,
I don't do it like that anymore. So.
Exactly, but you might, right? It's not like you don't do it anymore. It's just that you don't do it for your current project, right? There might be a project one day where your VIA array is not going to work.
I don't do it the method you were doing. So.
Yeah.
Anyways, people should go watch that video. It was a good video.
Come on, there's a very important point to be made here, and you're brushing it off. Is that the technique I was using is the better technique for some particular designs. It's not like, so you can't just say, oh, I'm never going to use that technique because I use the VIA array or I use the VIA button or whatever. That's wrong.
I'm saying that's not how I would do it personally, but I'm not saying it's a bad way to do it. I'm just saying I do it different.
Then you're going to be doing it the slow, painful way. Congratulations.
I don't think so, but
no,
okay.
I think you might be. Yep. Have you ever done a board where you have a whole bunch of VIA stitches, hundreds and hundreds of them, and then you want to copy them, and then you want to flip them and mirror them on the other side of the board? Ever done that? I have.
I have not done that because I actually have not been doing, I don't do...
You don't do professionally, not a professional PCB designer.
That's right. I'm not. Yeah, oh boy, I've learned that one a couple times.
That's it. There's tons of things that, like a high-end professional PCB designer would do that you would never see a hobbyist or an amateur do, or even just your regular engineer do on just a generic board, like a fairly, not a hugely complex board that takes you months and months to lay out. So, there's all these different things.
You're a little defensive, buddy. Little defensive.
No, trying to teach. No, you're dismissing a perfectly useful technique.
I'm not dismissing it. I'm just saying I'll do it different.
Brushing it off.
Anywho, it was a good video otherwise. What are you gonna do? What are you gonna do with that? So you were gonna send that board out. That was the one where you were making the EMI.
Yes, I sent it out. It's probably already manufactured.
Oh,
I should. Yeah, I've got the. I've got the gold on the edges so that I can put tape on later if I want to seal the edges up.
I think we mentioned that video though. I did like that EMI video you did with the different probes and stuff.
That was comparing the 2-layer and 4-layer board.
Yeah.
Well, this one's a continuation of that.
Yeah, right. I'm just saying is that something that you so in your design process, would you go and do the same kind of thing with your with the microsupply? Are you gonna do the same kind of like EMI detection on that thing before you send it out?
Oh, we will probably do some pre-compliance and stuff like that, maybe. Yeah.
Yeah.
Yep.
But I mean, like the same method
sure.
of just like waving the wand over it, or what else are you going to be doing
sure.
for that?
Yeah, of course. Yeah. I'll be doing all the usual stuff, I'll be doing the, just looking for spurs and things like that, anything that comes out of it, sure.
Cool.
Haven't done that yet. Probably should.
Yeah.
But, well, this is kind of like, we're hoping this is like the final prototype before it goes into production. So this is the one we have to do it on, and we're just in the process of building that up now. So we could have done the previous ones, but it was like, it's not,
Yeah, if things are going to be changing, it's like, when do you really start to do... Like, you wouldn't build a test fixture until you know your stuff's relatively finished anyway. So it's the same kind of thing. It's like you start to move from, beginning design to something more production ready.
Yep.
Yeah, you start to do the more manufacturing-y type stuff anyways.
But we've done pretty much the best we can in there by keeping, minimizing our loops and stuff like that. We pay particular attention to that, and it was very conscious in the design of it. So, so if there are issues, it's hard to make them better apart from shielding the whole damn thing, or doing something like that, right? So it's if it's a problem, it won't be because of a poor layout. Let's put it that way.
Mm-hmm. So, you're saying it'll just be something because some natural process or
it's just
like a switching
some
regulator
natural requirement.
Yep.
Has a spur at this frequency that then it generates harmonics at this frequency, and because of the your output has to be a certain lead length to get to the other side of your product. There's nothing you can do about it, kind of like short of, as I said, putting it in a shielded box or whatever. So, yep.
Yeah, that makes sense. Cool.
Anyway.
Well, practice makes perfect. And that brings me to my thing that I want to talk about is this book I've been rereading, actually, or listening to, I guess.
It's been reading another self-help book, folks.
I don't think this is, well, yeah, maybe it is.
Come on, self-help. You
Yeah,
just love reading this stuff.
I love self-help books.
Can't get enough.
Yeah, but this one actually, I got into this one
this
because...
one's different. Okay.
No, I got into this one because of teaching stuff. And so someone had suggested it for that. And so this is called the Practicing Mind, and it's it's a little, it's got like mindfulness type stuff in there as well. But the thing I like about it is it's kind of talking about
mindfulness type stuff.
So like meditation and basically being in the present while you're doing while you're practicing things.
Right. So sort of like I don't know, tantric PCB layout or something. I'm
there
sitting
you
there
go.
with my legs crossed on my yoga mat, with my laptop in front of me going, as I do a downward dog while I'm laying out my board.
Downward sloping trace.
Right. Yes, go on. Sorry, I was taking the piss.
Okay.
Yeah.
But yeah, actually, one of the things that he brings up is he talks about kind of getting into flow states and stuff like that, and how important that is for beginners versus people who are more
mental
advanced.
Flow states or process flow states?
Mental flow states. And I was actually thinking about he talks about how that's your best time for practicing, and I was thinking about when you're doing a layout and you look up and it's like 4 hours later, and it's that that same kind of like mental flow state type of thing. And so it's just about the joy of practice, and I don't know, and like maintaining good expectations as you're learning. So I think about this stuff because I'll watch YouTube videos of other people, yourself included, and I'll be like, oh man, I can't do this or that, whatever, and it's tough because then you focus more on the end goal than the process. But it's really it's about designing a process and a practice that you are regular about and you kind of keep focused on. So if you want to get better at layout, you don't look at an advanced, you don't look at an 8-layer PCB layout and say I can never do that. Right. You start with focusing on a 2-layer PCB and just what you need to learn right now. And so I don't know. It's a cheap audiobook. I recommend it. It's good for people that are getting started. It's applicable, obviously, much more than just electronics. The guy talks about golf and piano learning and a bunch of other stuff, archery and all these different things. But I think that it actually is applicable to the electronics world and the people that are listening to this, because it's if you want to get better at electronics, you have to kind of develop a practice. And you and I don't even really talk about that because we're well, you're obviously much more advanced than I am, but I've been doing this a while now too, and it's like, but you think about when you're getting started, like people that are getting started just even soldering, right? Like people that want to learn how to solder, they sometimes go out and buy like solder practice boards, and I think that's a great idea because then it's like a very regular practice of trying to do the same joint, getting a good looking joint over and over again. That's like a practice versus just going to solder something and then being frustrated when it looks bad or it doesn't work. So it's like developing skills and practicing around those skills versus just focusing on these end goals. Yeah, a little bit self-helpy, but it's a good book. I think you might like it.
So you can get is it spoken by the author?
It is. Yep. Yeah.
I only like audio books that are spoken by the author.
Oh, really? There's this this.
Oh, there's probably exceptions to that.
Well, there's this sci-fi series. I'm on the 4th book of The Expanse. It's actually a Amazon show right now too. And the actor that reads the books, oh man, he's such a good voice actor. He does like 20 voices throughout the book. One actor does all the voices. So in that case, a little bit different. But I agree in general that like I like when the author reads the book because then you like get their kind of feel to it.
Yes, exactly. Cool bananas.
Yeah.
So you can either buy the audio book or you can just go build stuff.
Sure. Yeah, you could just take what I just said right there and use that as. I don't think that's quite the same, but you could. Yeah. Right. I just wanted to point out because I know a lot of people are, like even though we have a lot of people that are listening that are very advanced, I think there's a lot of people that are listening that are just getting started as well. True. It's everybody's at a different spot.
Agreed.
In order to get more people that are just getting started, I'm going to ask for something that we have not asked for in a really, really long time. Like, I don't know, years. If people are listening and you like this show, can you go give us an iTunes review? We haven't had we've had iTunes reviews and people do that stuff, but we haven't asked for that in a long time. And if you're thinking about it, and I think it's easier now that like Apple Podcasts is the thing, if you could write us a note or give us I think so. I think because the Apple.
I don't have Apple anything, so I got no.
Right, I don't either. But like that's a large portion of the podcast audience is people that are listening via Apple Podcasts, and I think it's easier to do ratings through that now. And so, if you can give us a rating, that'd be great.
Yes, please.
If you know another nerd who might benefit from listening to us, we love that too. So. And
I presume that that bumps us up the algorithmic index.
Sure, but
somehow.
Yeah, I'm not really sure how it all works, but I think it helps. But I mean, people telling their friends as well, that'd be great. We always appreciate it. We're not like looking for, we don't need to conquer the world with the amp hour, but we'd love to teach more people, and that's what we hope for here.
Cool bananas. Even though you shot me down before for teaching a different technique.
Oh man, so butthurt. Oh my god. 9 years in, we still got it. Oh boy. Dave, you are a valuable contributor to the electronics world, and I respect you, and I'm grateful for you, Dave. Thank you for helping me practice patience today, Dave.
Oh my god.
All right,
we better go now.
Talk to you soon.
It's getting pathetic. Catch you next time.